For our fourth lesson, this is going to be a bunch of information and not a lot of example, all right? But there will be explanation, and so if you're just writing the things down and you're not listening to the explanation, then you're robbing yourself of the full understanding here. So I want to make sure that you see this. This one is going to be the most first semester looking lesson that we have of probably this entire semester, all right? So just keep that in mind. It's not that this is tough, it's just that we're going to be thinking, and thinking is generally harder than just following directions, right? So we've kind of learned over the course of the last semester that when we have a specific set of steps to do, we execute those steps usually pretty well. When it comes to thinking, that's what we're training you to do over the course of first semester, and so it's a hard thing for many of us to handle, but we're going to do our best work to think through so that we can prove that a quadrilateral is a parallelogram. The explanation is going to be supported, undergirded by geometric proof, all right? So we are proving that quadrilaterals are parallelograms. Obviously not all quadrilaterals are parallelograms, but if they have certain characteristics, we're going to look at their sides, angles, diagonals to see if the figure that we have is actually a parallelogram. Regardless of the way it looks, they may look like a parallelogram, but they might not be. They might not look like a parallelogram to our eyes, but based on the information, are they parallelograms? And so this is a little bit harder because it requires thinking. All right, so from lesson 3, we explored how the opposite sides in a parallelogram are congruent, how the consecutive angles in a parallelogram are supplementary, how the opposite angles of a parallelogram are congruent, and how the diagonals of a parallelogram bisect each other. The fun fact is that if we think about these in terms of conditional statements, if we have a parallelogram, then these things are true. Then the diagonals are congruent, the diagonals bisect each other, the opposite angles are congruent, the consecutive angles are supplementary, and the opposite sides are congruent. And so thinking about them as conditional statements, if the figure's a parallelogram, then these things are true, all right? So have that information down, have that last review down, just so that we can kind of coordinate this information and think of it not just in an if-then capacity, but in reverse as well, because the reverse is true, all right? We can write each of those statements as a biconditional. A quadrilateral is a parallelogram if and only if the opposite sides are congruent. A quadrilateral is a parallelogram if and only if the consecutive angles are supplementary. A quadrilateral is a parallelogram if and only if the opposite angles are congruent. A quadrilateral is a parallelogram if and only if the diagonals bisect each other. So what we're exploring here in lesson 4 is the converses of each of those previous theorems. So we had theorems 7, 8, 9, and 10. Here we're going to start with theorem 11 and we're going to move from there. If the opposite sides of a quadrilateral are congruent, then it's a parallelogram. So if we have this situation, then we can show that this is a parallelogram. Is the proof on the next slide or do I do it now? The proof is on the next slide. All right, so what we're going to do is I'm going to draw a diagonal in, and then by side, 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 I can show that we've got two congruent triangles, which means that we've got corresponding parts congruent. So if I draw in this segment, then that side is congruent to itself, and we have a pair of sides and a pair of sides given, right? This is the context. If we have congruent sides, opposite sides, then the figure is a parallelogram. So we're given that these sides are congruent to each other. When I draw in that diagonal, I have congruent triangles by side, 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 which means that these angles are congruent by CP/CTC, and these angles are congruent by CP/CTC. Well, folks, if those angles are congruent, then that means that these segments are parallel by the converse of the alternate interior angles theorem, and these segments are parallel by the converse of the alternate interior angles theorem. So again, thinking about these forwards and backwards. Write that information down, write that proof down. We also know that if we have supplementary consecutive angles, then that means that our quadrilateral is a parallelogram. Again, here it is, the separate theorems. Here it is as a biconditional. We're going to prove this one in your notes. You're going to try to prove this one in your notes. If this angle and this angle are supplementary, then how can you show that this is a parallelogram? I'll give you a hint. You're going to use the converse of the same side interior angles postulate. That's going to be the reason for saying that the opposite sides are parallel. Can you write that out as, it would probably be a 4 or 5 step proof total to show that both pairs of sides are parallel, and therefore the figure is a parallelogram. All right, so again, you do this, you proof. It's going to be for points, right? So you want to make sure that you do that, so you can get full credit on your notes here. All right, Theorem 613. All right, if both pairs of opposite angles are congruent, then that quadrilateral has to be a parallelogram. So if these and these, not just one pair, but both pairs of opposite angles congruent, then this is a parallelogram. The proof on this isn't so bad. Essentially what we will do, is we will draw in a diagonal, and what we're going to show, actually, we're going to use the previous theorem on that. It's actually going to be a little bit easier. If these are congruent and these are congruent, then what we can do with that information is show that all of those angles have to add up 2 x's and 2 y's. If these are x's and these are y's, then 2 x's and 2 y's are going to add up to 360. That means x plus y is going to equal 180. So that means that our consecutive angles are supplementary, and therefore by the converse of the same side interior angles postulate, the opposite sides are parallel. So really we're going to continue the proof from theorem 612 to do our proof of theorem 613. And then finally, if the diagonals of a quadrilateral bisect each other, then this quadrilateral is a parallelogram. Do I have that proof? I do not have that proof, so I will write that out. So if these bisect each other, boop and boop, then we can say that these that this figure is a parallelogram. We're going to use side angle side using the given, not given, but definition of bisect there. Then we can say that these angles are congruent. So by side angle side, these triangles are congruent. Also, these sides are congruent, but we're just going to do one side at a time. And if we show that these are congruent, then that means that their corresponding parts are congruent, which means that these lines are parallel to one another. If these angles are congruent also by CP/CTC, then that means that, that's the same pair of sides. I'd have to show that the other pair of triangles is also congruent. I thought I was special. I thought I was getting ahead of myself. If I show that these angles here are congruent by vertical angles theorem, then we have side angle side for this pair, and therefore by CP/CTC, I can show that this and this are congruent, which means that these lines are parallel by the converse of the alternate interior angles theorem. So you're going to use converse of alternate interior angles after using CP/CTC, after proving 2 pairs of triangles congruent by side angle side. Sorry that one was a little more drawn out. But again, the punchline there is that if we know that the opposite sides are congruent, then we have parallelograms. If we know that the opposite angles are congruent, then we have a parallelogram. If we know that the consecutive angles are supplementary, then we know we have a parallelogram. If we can show that the diagonals bisect each other, or if we're given that the diagonals bisect each other, then we can show that we have a parallelogram. All right, so that's all working in the context that we don't know it's a parallelogram, so we can't use rules from parallelograms, but we have to do triangle congruence, and then CP/CTC, and then converses of our theorems from chapter 2. So if you're stuck on some of those converses, I would re-watch lesson 2.2 from last semester. Scroll back in Google Classroom or scroll back on my channel and you will find that explanation. The last thing is not a converse of something else, but it is a proof that we've done about a dozen times. And so here, theorem 615, this is the last batch of information. If one pair of sides is both parallel and congruent, then the figure has to be a parallelogram. Based on this information, what we see here is we have a pair of congruent sides, a pair of parallel sides. One pair of sides parallel only means that we have a trapezoid, right? But if that pair of parallel sides is also congruent, then it cannot be a trapezoid. It must be a parallelogram. And the proof of that is what we did a bunch in first semester. All right, using the alternate interior angles theorem and a reflexive diagonal, we show that those triangles are congruent by side angle side, and therefore from there we can show that the other sides are congruent, and so that means that we've got both pairs of opposite sides congruent, which means it's a parallelogram, or we could use that these angles are congruent by CP/CTC and show that the opposite sides are parallel, or the other pair of sides is parallel by the converse of the alternate interior angles theorem. So that again is something that again only is working backwards, but having only one pair of sides congruent and parallel. All right, so this is a great summary. Please write this summary down again. Parallel, if you have a parallelogram, then these things are true. If these things are true, you have a parallelogram. Likewise, if you have a pair of sides that's parallel and congruent, then that figure must be a parallelogram. So obviously a lot of information here. We didn't do examples where we said, hey, if these are congruent, then they're going to have the same measures, and then we use those numbers and blah, 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 blah. But the work that we're going to do is going to look a little similar to the work that we did in lesson 2.2. And lesson 2.2 was again a little bit backwards because we were maybe posed the question of what value of x would make this figure a parallelogram. And so essentially we're doing the same work that we did in 6.3, we're doing the same work, but it's different thinking. Likewise, lesson 2.2 was a little bit tough because we said, what do we need to know to show that this is a parallelogram? And so we have to think about all of those perspectives. Just like in lesson 2, we had to think about what did we need to make sure that these lines were parallel, or given this information, are these lines parallel? And so that's obviously a different level of thought, and so it's harder because you have to think. And I know that's the overall struggle that we're dealing with in geometry, is that it's not just follow the steps, it's not just follow directions, it's understand the facts, use the facts to make a case, to prove your case. Hopefully at the end of this conversation, and if not at the end of the conversation, hopefully at the end of our class practice, you will be able to use the properties of sides, angles, and diagonals in a quadrilateral to identify whether or not we have a parallelogram.